Okay, hello everyone. In this lecture, we will study the prime number theorem, and we're not going to finish the whole proof, but we will introduce zeta function and study some basic properties of zeta function, like the functional equations and the meromorphic extensions, and where's simple pole, where's singularities, where is zeros. Okay. Prime number theorem. So we introduce some special counting functions. I think the idea comes from probably Chebyshev, and much earlier we have Dirichlet, Euler, Gauss. So this is pi x is a number of primes less than x. So the prime number theorem claims that pi x is almost equal to x log x as x goes to infinity. This theorem is pretty significant. I think the first proof probably are given 100 years ago, but the result already known to Gauss, at least to Gauss, by computation. And actually, so I'm not an expert in number theorem, but I heard that the Riemann hypothesis, so you see here you have the first approximation, then Riemann hypothesis more or less equivalent to decide what is the next term, to decide the higher order terms. Okay, and to prove the prime number theorem, although we will not prove it, but I would like to introduce some basic tools. So first, this is called the Dirichlet series and Dirichlet function. So suppose you have two set of numbers defined. Cn equals m. For all pairs of mk equals n, you have bm times am times bk. And then you have a sequence of Cn. Or equivalently, you can view this way. Suppose you have am divided by ms and times summation k from 1 to infinity bk, k to s power, and then you define it to be Cn divided by ns. And then example, if you choose a coefficient to be 1, then you have the famous Riemann Zeta function. I think the analytic method was introduced into number theory by, first let's write down it. It's introduced into number theory first by Dirichlet, who proved that there are if A and B are coprime, then there are infinitely many primes in ax plus b for A equals 1, 2, 3, all the way up. Co-prime numbers natural numbers for simplicity. Okay, this is actually if you use some algebraic method, like what the ancient Greeks do, prove that there are infinite primes in natural numbers, then you cannot get the result. Dirichlet gets the result by his famous Dirichlet series. Okay, then next we will focus on the study of the zeta function. So proposition 1, zeta S can be written down as the following. Product, and this is because each natural number has a prime decomposition, can be decomposed as a product of prime. Then you have this one, and then if you sum them up, you have 1 minus 1 over p to s power. This is called the Euler product. And then remark, it's not related to the material we're going to prove, but it's related to the current research field in mathematics. So probably you heard there's a Lens program. So you see here, zeta function has a Euler product. The natural question is, which automorphism function has a Euler product? A natural guess is Lens discovered that if you associate with some representation, then it has a Euler product. This is just a very shallow introduction to the Lens program. It's much deeper than I think. Okay, then proposition 2. I'm not going to prove this. It's just elementary number theory. Then you have gamma s times theta s times zeta s minus m, which equals m from n to m, sigma m n, n to nth power. So sigma m m is defined by m's power, summation of m's power of all the factors of n. This is also elementary number theory, so I'm not going to prove it. Okay, then proposition 3, negative d ds log theta s is negative zeta prime divided by zeta. And so by the Euler product form, you can derive that this will be another Dirichlet series. But now gamma n is log p if n is p to m's power and 0 otherwise. And there are some other arithmetic counting functions. So for example, in the proof, you will study this kind of thing. So summation of gamma n less than x. So you see which will be summation of all number p, a prime number p such that pm less than x. Okay, so what should I say? I should say in this way. So for each number has a form p to m's power less than x, then you give it a value log p and you sum them up. Okay, next we will focus on the Riemann's zeta function by the complex analysis. So first, we noted that this function is well defined and holomorphic for complex numbers with real part greater than 1. You can prove it by taking Cauchy-Riemann derivatives and prove the convergence of the derivative. And then the natural question is just like what we did for gamma function, how to extend zeta z to the whole complex plane as a meromorphic function. And then if you think about what we did for the gamma function, probably we need to have some integral representation. Okay, so those are done by Riemann itself. So let's consider the following integral. And then of course you can expand it to summation and from 1 to infinity t z minus 1 exponential negative nt dt. And then if you change variables, then you will find this is a summation and from 1 to infinity 1 over z to n's power summation integration from t to equals 0 to infinity t z minus 1 exponential negative t dt. So this is gamma z zeta z. So especially this is true for z so if you consider the convergence, it's true for a complex number with real part greater than 1. Okay, then let's rewrite it. Then for real numbers, you do have this formula as real number greater than 1. And then we want to extend this to holomorphic functions by changing z to s to z, but still you may have some non-convergence situation, so we change a little bit. We define zeta z by negative 1 over 2I sine z pi times gamma z integration negative omega z minus 1's power to exponential omega minus 1. So here you have loop c d omega. And then if you draw a picture, what we did is the loop we are interested in is one from positive infinity to negative infinity and the circle around 0. And finally, we will shrink the curve all the way. Okay, so let's call the radius is epsilon. Later on, we will let epsilon go to 0. And here, since you have power function, then we take the cut like this, and then your function is defined in the remaining part. Okay. So here the theta, so omega is rho ei theta, and we let theta be an angle between 0 and 2 pi. So that corresponds to the cutting. Okay, next proposition. Zeta z coincides with Zeta S, which is defined 1 over n to s power when z equals s. Okay, for real part s greater than 1. Here probably I should okay, I use a hat here to represent the one defined by the integration, and without hat we indicate the zeta function defined by the summation of power functions. Okay, so proof. So first, let's look at the power function. So it's easy to see the power function now is defined by exponential s minus 1 log negative omega. So exponential s minus 1 log rho and the plus. So the angle will be I phi minus pi. Okay, then let's look at the line integral. So we can decompose it into two pieces, and after take epsilon to 0, of course you can estimate the far away part and the small circle part. You can estimate this part. When epsilon goes to 0, integral goes to 0. And then you see since so let me draw another one. Since the blue one and the red one has the integration are the same, because the Cauchy-Coushac theorem at the far away part, the integral goes to 0. Therefore, this will be the same as integration. The above one is from infinity to 0, exponential z minus 1 log rho minus I pi divided by exponential rho minus 1 d rho, and then you have the bottom one is exponential s minus 1 log rho plus log rho plus I pi divided by e rho minus 1 d rho. And you simplify it. So this is in the index. Minus I pi. Simplified, you have exponential s minus 1 pi I minus exponential negative s minus 1 pi I. Integration rho from 0 to infinity exponential s minus 1 log rho exponential rho minus 1 d rho. And this is the same as negative 2i psi pi s times gamma s zeta s. Okay, next then we can extend the integration, the zeta function, zeta s for real part s greater than 1 by zeta hat s. Zeta hat z, where zeta hat z is defined by this formula. Now we try to simplify it a little bit. Notice that gamma z times gamma 1 minus z is pi over sine pi z. Therefore, you can cancel out the sine pi z part, and you have this will be I gamma 1 minus z 2 pi integral negative omega z minus 1 e omega minus 1 d omega around the loop C. And for this one, it's easy to see that it's convergent for all number z different from the poles O. So let's see, if 1 minus z is not a pole O gamma 1 minus z, this is holomorphic. And actually the second factor is holomorphic. Therefore this, and notice that this is meromorphic, which we'll prove before. Therefore zeta hat z is meromorphic on C. In the following, we denote the extension just by zeta z. So next we will, what is the singularity, what are the singularities of zeta z. So proposition for 1. So the integral negative omega s minus 1 e omega minus 1 d omega is holomorphic for all S in C. And the pole set of gamma 1 minus S is also, we just directly prove this, is holomorphic, and the pole set of this is, we already showed that 1, negative 1, negative 2, or S equals 1 to n to infinity. And also gamma 1 minus S has simple poles only. And on the other hand, Zeta S is holomorphic for real part S greater than 0 by the first definition as a summation of power series. Then Zeta S has at most a simple pole at S equals 1. Recall that we have expansion gamma 1 minus S is minus 1 S minus 1. Therefore, the residue of Zeta S at point 1 is I over 2 pi times residue S equals 1 gamma 1 minus S times the integral 1 minus omega S minus 1 e omega d omega at S equals 1. Okay, then find is I over 2 pi negative 1 and times 2 pi I equals 1. So we know that the proposition is gamma S has a simple pole at S equals 1 and holomorphic for all S in C as different from 1. Okay, next we are going to determine the so-called trivial zeros of Zeta S. So assume S is a non-positive integer. Then we do the expansion of the following function. We find the first filters is 1 minus half omega. Then you have the so-called Bernoulli numbers. Bernoulli numbers. And if you do the line integral, so you have this will be integration of 1 minus negative 1 S minus 1 divided by 2 omega S minus 1 plus n equals 1 to infinity minus 1 S plus n Bn omega 2n plus S minus 2 n factorial d omega, and then it will be 2 pi I. We compute the residue omega equals 0. Of course, here you need to work a little bit. So because the loop C is not closed, why this equals this? First, before you do expansion, you need to first complete the loop. Okay, so I will omit this part here. So negative 1 s minus 1 2 omega s minus 1 plus n from 1 to infinity, negative 1 s plus n bn omega 2n plus s minus 2 divided by 2n factorial. And then you have three possibilities. If s is 0, then this is pi I. If s is negative even numbers, it's 0. If s is negative even numbers, negative odd numbers, is 2 pi I negative 1 plus m divided by 2m factorial bm. And also notice that since s is a non-positive integer, then gamma 1 minus s is just negative s factorial. Okay, then from zeta s equals I gamma 1 minus s divided by 2 pi times line integral. It follows that s equals negative 2m are the trivial zeros of zeta z. Okay, actually, except the trivial zeros, people expect are expected on the real part z equals 1/2. So this is called the Riemann hypothesis. And the prime number theory from the proof is more or less equal to confirm that real part z equals 1 is free of zeros. There's no zeros on this line. And the current status of the problem is that so this is a line z equals 1. So people know there's no zeros outside those regions. Okay, and the ultimate goal is to prove, if we can, real part z equals 1. Real part z equals 1/2 here. To prove they're all on the line, on the red lines. But then no matter how clever the people is, nowadays, they can start with some small stripe, but eventually it will close to the line 1. So it's not clear even today. Can we prove that zeta s different from 0 when real part s greater than 1 minus epsilon? Epsilon is some positive number. It's not clear even today. Not even never mentioned the Riemann hypothesis itself. Okay, if you are interested in this, I suggest you to read Ivanish's textbook and Teacher March's textbook as well about the Riemann hypothesis. Okay, next we will study the functional equation of Zeta S. Although we are not able to prove too much about zeta function, but we still can do some algebraic theory about zeta function. We can derive the functional equation and use that to do some representation theorem, etc. So the functional equation, one of the functional equation is zeta 1 minus z is 2 to power 1 minus z pi to negative z cosine pi z over 2 gamma z zeta z. So to prove this, for z with real part z less than 0, we use the integral representation times gamma z integration c minus omega z minus 1 exponential omega minus 1 d omega, and then deform the contour to Cn, which starts with positive. Okay, so I would rather to draw the picture instead of writing down. So you start with infinity and goes above the real axis to 2n plus, so this is 2n plus 1 pi, and then go to anticlockwise. And all the way back. Of course, you still have the cutting here along the positive direction. So those coordinates are 1 plus I, 2n plus 1 pi, 1 minus I, 2n plus 1 pi, negative 1, negative I, 2n plus 1 pi, negative 1 plus I, 2n plus 1 pi. Okay, and note that you have some poles along the imaginary part because of E omega equals 1. So next, so recall that poles of negative omega z minus 1 divided by E omega minus 1 are 2 pi I z minus 0. Okay, and so you draw it here because the other contour go this way. This is your C, pretty close, but never touch the positive real axis. And then you deform this, means actually the green part plus the blue part plus the green part, and the integral along this should give you the residue inside it. Okay, so where's the residue? Because in your region, the poles are along the imaginary y-axis is. Okay, then also we can compute the residues of negative omega z minus 1 exponential omega minus 1 d omega. So if you expand it, what do you have? This is exponential z minus 1 log 2m pi, because omega is now at the pole, so it's 2m pi I, so log 2m pi and minus 1/2 pi I. This is the angle, and in the denominator, since you have omega, e omega minus 1 is omega, so the residue just this part, this is the coefficient. This is the residue. This is the residue. Okay, if you compute it, so this equals 2m pi z minus 1's power times I times exponential negative 1/2 pi I z. This is for all omega equals 2m pi I, m greater than 0. Similarly, if omega is negative 2m I pi, m greater than 0, then the residue is e z minus 1 log 2m pi plus 1/2 I pi equals negative 2m pi z minus 1 I exponential 1/2 I pi z. So sum them up, you have the residue is 2m pi z minus 1 times 2 times psi half pi z. Therefore, we have that. So on this side, so let's see. You times this part to the other side, and notice that the integral of the green part goes to 0 when n goes to infinity. Therefore, the integral of the blue part of the minus omega s z minus 1 divided by e omega minus 1 is the same as summation of residue. Okay, therefore you have negative, so let's times this to the other side, negative 2i sine z pi times gamma z zeta z equals negative 2 pi I summation m from 1 to infinity 2m pi z minus 1 sine pi z over 2, and this equals negative 2 pi I 2 pi z minus 1 zeta 1 minus z times 2 sine so here you have 2, sorry, sine pi z over 2. Okay, and use trigonometric function, you can write this as 2 sine z pi divided by 2 and cosine pi z divided by 2. Therefore, finally, you have zeta 1 minus z is 2 1 minus z pi minus z cosine pi z over 2 times gamma z zeta z. And also recall the duplication formula for gamma function. So you have gamma s is 2s minus 1 gamma s plus. So this is done by for the functional equation. Next we will do some variation of the functional equation so that it has a little bit better form, which shows symmetry about the functional equation. In other words, we are going to give some geometric interpretation of the functional equation. Okay, then you have this, and then you plug in, you find zeta 1 minus s is pi negative s minus 1 half gamma s plus 1 over 2 gamma s over 2 cosine pi s over 2 zeta z. Zeta s. We use the same notation. And then pi negative s minus 1 half. And then use the duplication formula. You can combine. Use the formula cosine pi z over 2. Pi s over 2 is this is pi over gamma 1 minus s over 2 gamma 1 plus s over 2 zeta s. Okay, then it's pi negative s over 2 1 over pi negative 1 minus s over 2 gamma 1 minus s over 2 gamma s over 2 zeta s. And you move the denominator to the other side, you have a pretty symmetric form of the functional equation zeta s. So if define c s as 1 half s minus 1 gamma s over 2 pi minus over 2 zeta s, then it's easy to see c1 minus s equals c s. The reason we times this extra factor here is because after time this factor, c is entire. It's holomorphic on the whole complex plane. Then this will be a nicer form. But the disadvantage of this nicer form is probably in number theory, it's not so close related to the prime numbers. You do have some transcendental factors here. Okay, especially you have this guy here. So it's not so close related to the number theory. But geometrically, it just tells you the functional equation. Whenever you have functional equation, it's a problem. It's a matter of symmetry. Therefore, it's related to the representation theory. Okay, next you can look at the textbook for the proof. I think you still have probably half of the half of the chapter to finish the section to finish it. If you want the proof of the prime number theorem, I will not give the proof here, so I will stop here.